Okay, so let's take a look at some interesting functions. Let's first take a look at sine of x over x. Now notice that if I try to plug in 0, so if I try to find f of 0, I would get sine of 0 over 0. Now obviously this right here, this does not exist because you can't divide a number by 0, so this is impossible, but it is an interesting kind of undefined function. Notice that this is equal to, if you plug in 0, you get 0 over 0. Now later on we're going to learn that this is a type of what we call an indeterminate form. And we'll talk later about why that's important, but for now let's take a look at the picture. And so here I have my function, sine of x over x, and so if you look at it, you know, it's a it kind of looks like sine, except that over time it's attenuated. So it's getting smaller and smaller over time. But notice that the value that we were looking at 0, this function, it looks like it equals to 1. But how does that work if we already know that you can't actually plug in 0? So let's zoom in. It still looks like it's going to 1. If you zoom in a little bit more, you see it's pretty obvious that it's going towards 1. And so the key here is that the limit as x approaches 0 of this function is equal to 1, even though at 0, at x equals 0 itself, the function does not equal to 1. And so let me give you a little graph of this guy. So here's the attenuation. And then at x equals 0, there's actually a hole there. There's a hole that's not shown in the graphing, and if you try to graph it using your calculator, you'll notice that you won't. It doesn't look like there's a hole either. But it's obvious that when x equals to 0, this guy is undefined. But as x approaches 0, so the limit as x approaches 0 of your function of sine of x over x, this is equal to 1 because both from the left side and the right side, as x approaches 0, that function is going towards 1. Okay, let's look at another interesting function. You'll notice that this function also, if you try to find, if you try to plug in 2, you'll get that this guy is also undefined, 0 over 0. So let's take a look at the picture. If you graph this guy, you'll notice that when x is greater than 2, so 2 is right there, this function is equal to positive 1, but when x is equal to negative, or less than 2, sorry, this guy equals to negative 1. So the limit this time doesn't exist because when you come in from the right side, it's approaching positive 1. But if you're approaching from the left side, this guy equals to negative 1. So this limit doesn't exist. So this guy does not exist. Now we're going to talk about how to do these algebraically later, but for now we can see that graphically it doesn't exist. Now how about we take a look at another interesting one. How about the limit as x approaches 0 of x squared minus 4x over x. Now, if you remember from pre-calculus, this is looks like a rational function, right? And rational functions, remember, if I just graph the very simple, simplest rational function, 1 over x, it looks like this, right? It's got a horizontal asymptote at 0. It's got a vertical asymptote at 0. And so we expect this guy to look somewhat similar. Now, obviously, if you plug in 0, you'll notice that you get 0 over 0, which we already know that's indeterminate. We don't know what that means yet, but we know it's indeterminate. But let's graph it. And so you'll notice that this doesn't look like a rational function at all. This looks exactly like a linear function. And obviously we don't see the whole because it's not capable of showing us the whole, but it's not defined here at 0. So let me just try to show you what's happening. Notice that there's a different way of writing this function right here. Notice that x squared minus 4x over x, you can also write it as x times x minus 4 over x. And so what we just found out is that this guy is equal to x minus 4. So this function right here is equal to x minus 4, which is a line, which is exactly this line right here. This is the line with a y-intercept of -4 and a slope of 1. That line, except that if I graph this line, it's not actually defined at 0. So you have to be careful, because this guy right here is a line with a y-intercept of -4, but there's a hole here. So this line right here, you have to also add in that x can't equal to 0. So this function, x squared minus 4x over x, is the same as x minus 4, except that you have to remember that x can't actually equal to 0 here, because it can't equal to 0 here. So that's important to keep in mind. But otherwise, these two functions are exactly identical. They're exactly the same, except that it is not defined at 0. So when you take the limit as x approaches 0, and you're approaching 0, you know that you're going towards the y value -4, because both when you come in from the right or the left, the y value that you're approaching is -4. Now we can see that from the picture, but notice, now this is going to be key for later, we can also notice it from right here. So essentially what we're saying is that if you can convert your function into a form where you can actually plug in the number, so here you can't plug in, you can't plug, but here you can plug. Plugging in 0 is okay here. What that'll tell you is it'll tell you where it's going. So that doesn't mean that we are saying that 0 is defined for the function. That just means that this guy right here tells us at 0 that this function is going to -4 without necessarily having to graph it, and that's important. Okay, so what we just got from that is a very important basic rule for finding limits. And to do that, I'm just going to write down the rule So this is before, we haven't really rigorously defined continuity. But most of you guys intuitively know what that means. So I'm just going to use it anyways. But we're just going to say that if your function is continuous, at a point, let's just call it a, then the limit as x approaches a of your function is equal to f of a. Now this is just another way of saying the definition of continuity, which we're going to go over later. But what we're essentially saying is exactly what happened right here in this example, is that you have a function that isn't continuous. It's got a hole here, so it's not continuous at 0. So what you do is you convert it into a function that is continuous. This is a continuous function, x minus 4. And although these aren't the same, this one you can plug in 0 and it'll tell you where this one is going. So let's write that down as a series of steps. So to find limits, algebraically. Okay. Step 1. First thing you're going to do is you're going to plug in the number. Okay. So because we know that if it's continuous, then plugging in the number, we're done. Okay. So put in parentheses, if it works, you're done. That means the function was continuous and there's nothing else to do. Now if you get an indeterminate form, I'm just going to list a couple. 0 over 0 is an indeterminate form. Infinity over infinity is another indeterminate form. You've got 1 to the infinity is also an indeterminate form. You've got infinity minus infinity. And you've also got infinity times 0. Okay, so any of those, and what this means is you have to do more work. So if you get one of these, you have to do some more work. And we're going to show with examples what that means. So you basically do some algebra. So some of the more work stuff could be factoring. Sometimes you have to rationalize, and etc. There's different cases, and we'll go over quite a few of them. Okay, and then or you can also get a constant over 0, and this isn't indeterminate, but what this means, this we'll deal with later, but what this means is that it's going to infinity or negative infinity. Because what's happening is the top is going to be a constant, and then the bottom is going to be going towards 0. So it's like if you're have a constant number 4 and you're constantly dividing by a smaller and smaller number, this whole thing is going to be blowing up and get bigger and bigger and bigger. So it's going to go to either infinity or negative infinity. So we'll talk about that case in a bit as well. So let's do some examples.